Hello everyone, my name is Kyoung. I'm a server-side engineer of live messaging platform team. I'll be introducing a new scalable social relation called follow today. So here is the agenda. I'll start with introducing background information and some initial requirements. After that, I'll explain design details with 3 technical points. Finally, I will summarize the main points and show you improvements we are considering for the future. Then I will explain why we needed a new relationship. Originally, the only possible relationships online were friends. Line provided friend-based services such as messaging, calling, and viewing friends' posts on the timeline. Friends are close to each other, but the number of friends you can have is relatively small. Line's mission is closing the distance, and there has been an untapped demand to subscribe to other users' activities, though they aren't likely to become actual friends. To meet this need, we have introduced the new ability to follow. Through timeline discovery, you can discover people with the same interests as you. And popular influencers can also accumulate a large following to reflect their popularity on our platform. The follow relationship, though more distant than friend relationships, encompasses a much larger group. Unlike the concept of a friend, in a follow relationship, a huge number of users can subscribe to one user. So basically, the design has to be different from a friend relationship. When designing a system, it is important to clarify the maximum number of data. For example, the number of friends of regular users can be up to 5,000 people. According to this number, we can design an optimized storage structure from the point of view of the performance. Then, before designing a new system for the follow relationship, it would be a good idea to set the number as the reference point. The reference point we used when designing was more than 100 million followers. The reason we set the standard to more than 100 million followers was that there were already Line official accounts with over 100 million friends. Line official account is a different user type from general users. Unlike general users, official account stores the friend data in a separate storage structure. However, for the follow relationship, we plan to store the friend data of both general user and official account in the same storage, regardless of the type of user. There were many considerations while designing the system. The first consideration was the scalability. We need to increase the possible relationship size of the users, and the highest follow count should be about 20,000 times larger than the highest friend count. The second consideration was the data consistency. Line server usually stores the data in HBase and Redis for high scalability. But when using NoSQL database, we are more likely to encounter data consistency problems. We will explain the ways to maintain data consistency using the Line's open source framework further in the presentation. The third consideration was the event delivery. Line service consists of many components such as a messaging platform, timeline, and so on. So the platform server should deliver the follow event to the various components which need the event. Also, the reliability of this event must be reliable. Based on the considerations, we designed a scalable system. First, when saving data, we chose an optimized structure for massive records and high read performance. And we also cached anything that could be frequently requested by users. But because the structure consisted of multiple database tables and caches, we encountered a challenge regarding data consistency between them. So we designed our system to ensure eventual data consistency. And we also implemented reliable event delivery, which also plays an important role in ensuring eventual data consistency. The line messaging platform has been stably operating based on HBase, Redis, and Kafka, and there are many skilled engineers responsible for the reliability of the component. So follow storage also uses HBase for persistent storage and Redis for cache. And we also use Kafka with Decaton for event delivery and maintaining data consistency. Decaton is an open source framework developed by Line, which we will discuss later. Based on the design concept, we are currently stably operating the service. Before introducing the details, I will briefly introduce current service statistics. Currently, 6.5 billion follow relationships are stored in our database. And they are served to our users with an average API response time of 8 milliseconds. And up to 200,000 follow events per minute are being generated and processed without loss. We designed an optimized storage structure for massive records and high read performance. Indexes for following and follow lists are pre-generated, and they are stored in HBase index table in forms that can be read directly from the API. And the data is distributed as evenly as possible across the HBase region servers for scalability. Every user's following and follow count are also stored as long type values in the count table, so the database does not need to count them during runtime. Furthermore, the majority of the data is also stored in cache for the high read performance. Looking at this design, you may have some questions. First, you might be wondering how we will maintain data consistency between database tables and caches. Second, you may also wonder how we resolve the concurrency issue of the count table. First, I will explain how follow storage is maintaining data consistency. Line's open source framework Decaton plays a key role in maintaining data consistency. Follow storage uses Kafka with Decaton for various purposes, such as event delivery and maintaining data consistency. Decaton is a streaming task processing framework built on top of Apache Kafka. Decaton provides various useful features such as retry queuing, concurrent processing, and task compaction by extending Kafka's basic functionalities. Let me introduce the features of Decaton mainly used in follow storage. The first feature I would like to introduce is the retry functionality. Kafka consumers may fail to process the task due to various reasons, such as network issues or delayed database response. In this case, Decaton will enqueue the failed task again without blocking the flow. Second, the Decaton task processor can process records consumed from one partition at the same time. Because Kafka assigns each partition to exactly one consumer, the number of partitions is the amount that can be processed simultaneously. It is very difficult to accurately predict the future traffic from scratch. Adding more partitions could have side effects, and Kafka doesn't support decreasing the partition number. Furthermore, it is also inefficient in terms of hardware resources to create a lot of partitions in advance to prepare for the increased tasks of the future. Because Decaton supports concurrent processing of records from one partition using multiple threads, we can have flexibility to adjust the throughput and use our hardware resources efficiently. Third, property configurations of Decaton task processor can be changed dynamically during runtime using central dogma. Central dogma is also an open source maintained by Line, and it is a centralized, multi-master replicated, version-controlled configuration repository. Using this feature, we can change the thread count of Decaton processor during runtime according to the traffic. Even if there is a sudden increase in traffic, we can respond flexibly by increasing throughput. I mentioned in the previous slide that Decaton is in charge of retry in the task processor. However, failures can occur when processing a task as well as consuming it. Kafka retries by default when it fails to produce a task, but if it needs more retries than Kafka is set to do, there is also a possibility that this task will be lost permanently. So we are using an enhanced producer named failure logging producer internally. Even when exhausting Kafka's default retry attempts, the producer serializes the task to the local file system and retries with the daemon automatically. With the failure logging producer, our system can be guaranteed to eventually produce the event. The reliability of the Kafka cluster is also important. Line has an in-house Kafka cluster named IMF Kafka, which guarantees high reliability. For more details, please refer to the presentation of linedevday 2019. With the Decaton, the failure logging processor, and IMF Kafka cluster, we were able to implement reliable event delivery. Using reliable event delivery, follow storage can maintain data consistency between HBase tables and Redis caches. And we also can implement real-time following follower count. Furthermore, other components can build their own data by consuming the event. Let's take a closer look at maintaining data consistency. When a user follows another user, follow storage puts data in the HBase data table, the HBase index table, and the Redis cache in that order. But there is a possibility that the follow storage will fail to put data in one of these. We can guarantee eventual data consistency through the reliable event delivery. If it fails in the middle, the server produces a retry event, and the Decaton task processor consumes the event and retries the remaining flow. But you may have a question for this flow. We cannot guarantee when the retry event will be processed. So the next request may be processed faster than the previous retry event. Then is there any possibility that the Decaton processor can override the stale data? To solve the problem, we are using the timestamp related characteristic of HBase. Even if the next request was processed first, HBase sorts the versions of a cell from newest to oldest by sorting the timestamp regardless of the put order. Thanks to this characteristic, eventual data consistency can be guaranteed. The Redis cache implementation is a little different. The follow storage sets the cache only when the request has been processed without retry. When retrying the flow, the Decaton task processor simply invalidates the cache, and the cache will be set by next read. Through this flow, the latest data can be put into the cache when reading data. Next, I will talk about real-time count. As I mentioned before, every user's following and follow counts are stored as long-type values in the HBase count table for optimized read performance. The basic strategy is increasing or decreasing the count when follow actions occur. Looking at this structure, you may have some doubts. Although the read performance may be good, you may think that concurrency problems may occur while incrementing the value. Actually, a famous influencer's follow count can be a hotspot. We may be able to think of a very simple architecture that each request tries to lock and increments the count sequentially. But the resulting performance would not be scalable. Again, Decaton with Kafka can solve this issue here. Before we look at the detailed flow, let's first look at the characteristics of Kafka. First, all messages with the same key will go to the same partition. Second, each Kafka partition will be assigned to exactly one consumer. This means that the influencer's follow count events can be delivered to a dedicated consumer one by one in the order that they are in queued. When events are delivered to a dedicated consumer one by one in the order that they are in queued, we can avoid the lock contention issue. However, you may be wondering what would happen if an influencer's follow count event were flooding in a Kafka partition. In that case, it may appear that other users' events in the same partition could also be affected. Fortunately, Decaton supports concurrent processing of records consumed from one partition by multi-threading. We can also change the thread count dynamically during runtime according to the traffic. Furthermore, Decaton also supports a task compaction feature. If tasks are flooding, we can use the task compaction feature to combine the same user's task within a specific time window. But there is a possibility that the server fails to produce the event. In that case, the Kafka producer will try to produce the event again using Kafka's built-in retry logic. However, the retry count could be exhausted due to various problems such as network issues. As I explained regarding the failure logging producer, even when exhausting Kafka's default retry attempt, the failure logging producer serializes a task to the local file system and automatically retries with the daemon. Sometimes, the Decaton processor may fail to process the event. But thanks to the Decaton's retry queuing, the event can be eventually processed successfully. However, it is very difficult to make sure that the retry logic only inputs the data once. For example, if there is a network issue, Decaton processor may not be able to receive a response from the database, but the database might process the request successfully. Thanks to the HBase timestamp behavior, putting the record with the same timestamp multiple times doesn't matter. However, incrementing count twice can cause an unexpected inconsistency. To resolve this kind of unexpected inconsistency, we check count inconsistency when the follow list API is getting the list data. When the follow list is fetched from HBase, inconsistencies are checked while minimizing additional storage I/O for the sampled target. We produce repair events for each inconsistent count data periodically. When Decaton processor consumes the repair event, the processor fetches and counts the user's whole follow list and stores the right count again asynchronously. Lastly, I will explain how we will deliver the follow events to various components. I mentioned that we use the Kafka event to implement the real-time count. We can generalize the event format for multiple purposes. Generalized events can be used to deliver follow information to other components as well as the real-time count. For example, when user A follows user B, the platform server produces two events. The first event is a forward event. The Kafka key is from user A's user ID, and the event is enqueued to the Kafka partition assigned to A's user ID. The second event is a reverse event. The direction of the second event is the opposite from the forward event. And the reverse event is enqueued to the Kafka partition assigned to B's user ID. As mentioned in the previous slide, the reason we produce events in two directions is so that each user's count events should be processed one after another to avoid lock contention issues. The follow count Decaton processor consumes both events. The first forward event increments the following count of user A, and the second reverse event increments the follower count of user B. Other consumers can choose which events to consume based on their purposes. For example, Line Timeline's consumer consumes only forward events and ignores reverse events. And the platform server also provides follow list APIs. The APIs can be used to get specific users' follow list directly with the Line Channel API. The Line Channel is a gateway in charge of communication and authentication between components. Other components can build their own data by combining the follow events and on-demand follow list API calls. Let me summarize the main point. We implemented the reliable event delivery with the Decaton, the failure logging processor, and the IMF Kafka cluster. With the reliable event delivery, our system can maintain data consistency while storing a large number of records and ensuring high read performance. And our system can deliver the follow events to the various components with reliability also. Based on the design concept, we are currently operating the service stably. Lastly, I'll show you some improvements we are considering for the future. We've noticed an improvement point while running the service. First, even if one event is missing, another component has to read the whole list of the user to rebuild its own data. Second, if the component's database has to contain whole follow data, the component should fetch whole data before starting to consume the event. So we are considering providing rich APIs so that other components can query the follow data in more flexible ways. If components can get data by filtering and sorting directly in the format they want, they can use them in the service directly without building their own databases. Giving the other components as much flexibility as possible will be the platform's goal and challenge. And there are many other things to improve. Currently, our system is pre-generating necessary indexes. This structure is advantageous for scalability and high read performance, but not flexible. If we pre-generate more indexes for the other requirements from the various components, there is a drawback of updating many indexes when storing data. So we are thinking about creating secondary indexes in a more efficient way. And we are also considering an enhanced inconsistency checker for the whole data. Currently, we are checking inconsistencies only for the sample targets during runtime. So if data inconsistency occurs on frequently requested data, it is likely to be discovered. However, there is a possibility of inconsistency in data that are not frequently requested. So it will be better to check the consistency of the entire data. And we suppose that more influencers with a large number of followers, the more unexpected problems will occur. We will be happy to discover the unexpected issues in the future and will fix them by improving our system. This concludes my presentation. Thank you very much.